Optical Instruments. Introduction. The optical instruments are the devices which help human eye in observing highly magnified images of tiny objects for detailed examination, in observing very far-off objects terrestrial or astronomical. Microscopes and telescopes are common examples of optical instruments. The essential optical components of these instruments are lenses and mirrors. The images are formed by refraction through lenses and by reflection at mirrors. The eye and myopia. As you can see the structure of human eye, the main parts of the human eye are cornea, C, iris, I, pupil, P, ciliary muscles, M, convex lens, that is also called eye lens, retina, R, and optic nerve, N. The eyeball is approximately spherical in shape, having diameter of about 2.3 cm. Now we talk about myopia, which is short-sightedness or nearsightedness. It is that defect of vision due to which a person cannot see the distant objects clearly. The far point of an eye suffering from myopia is less than infinity. Myopia is corrected by using spectacles containing concave lenses. When a concave lens L of suitable power is placed in front of the myopic eye, then the parallel rays of light coming from the distant object are first diverged by the concave lens. Due to this, the concave lens forms a virtual image of the distant object at the far point F of this myopic eye. Since the rays of light now appear to be coming from the eye's far point F, they can easily focus by the eye lens to form an image on the retina. Concave lenses are used for correcting myopia should be of such a focal length that it produces a virtual image of the distant object at the far point of the myopic eye. The eye is far more delicate and perfect than even the finest photographic camera designed so far. Instead of converging lens system of the camera, there is a crystalline lens in the eye. This is held in position by the ciliary muscles. In front of this lens is a contactable diaphragm with a circular aperture near the center. This diaphragm is called iris, and the circular aperture is called pupil of the eye. The function of iris is to adjust and allow suitable quantity of light into the eye. The front transparent part of the hard outer surface of the eyeball is called cornea. It protects the inner delicate parts of the eye. Defects of vision. Hypermetropia.
A person having the defect hypermetropia cannot read a book clearly and comfortably, though he can read the number of a distant bus clearly. This person is having the eye defect called hypermetropia, that is long-sightedness. He cannot read a book clearly by holding it at the normal distance of 25 cm. He has to hold the book at a much larger distance to be able to read it.
In spite of all precautions and proactive action, our eyes may develop some defects due to various reasons. Some of the common optical defects of the eye are myopia or short-sightedness, hypermetropia or long-sightedness, presbyopia, astigmatism, phoreus. The camera. The photographic camera consists of a light-proof box at one end of which a converging lens system is fitted. A light-sensitive film is fixed at the outer end of the box, opposite to the lens system. A real inverted image of the object is formed on the film by the lens system. For a good photograph, the amount of light entering the camera has to be adjusted accurately. Following controls are provided in the camera for this purpose: shutter, exposure time, aperture control. Film speed, viewfinder, focusing control, depth of focus, exposure meter. Simple microscope or magnifying glass. A compound microscope is an optical instrument used for observing highly magnified images of tiny objects. It consists of a converging lens of small focal length. A virtual erect and magnified image of the object is formed at the least distance of distinct vision from the eye, held closer to the lens. That is why the simple microscope is also called a magnifying glass. Compound microscope. Compound microscope. A compound microscope consists of two converging lenses. These objective lenses have very small focal length and short aperture. An eyepiece has moderate focal length and large aperture. These two lenses are held coaxially at the free ends of two coaxial tubes at a suitable fixed distance from each other. The distance of the objective lens from the object can be adjusted by rack and pinion arrangement. A compound microscope is an optical instrument used for observing highly magnified images of tiny objects. Astronomical telescope. An astronomical telescope is an optical instrument which is used for observing distinct images of heavenly bodies like stars, planets, etc. Terrestrial telescope.
A normal adjustment, that is final image at infinity. Telescope is an optical instrument used for viewing distant object. The telescope consists of two lenses, objective lens of long focal length and large aperture, and eyepiece lens of short focal length. When the instrument is towards a distant object like a star, the objective lens forms a real inverted image AB of the object in the focal plane FO of the objective. The tube length is then adjusted so that the image formed by objective is at the focus FE of the eyepiece A. Virtual magnified image is then formed at infinity.
A terrestrial telescope is an optical instrument which is used for observing distinctly the magnified images of distant objects on Earth. In an astronomical telescope, the final image is inverted with respect to the astronomical objects are spherical. But in a terrestrial telescope, the final image has to be erect. Reflecting type telescope. Cassegrain telescope. It is an improvement over the refracting type astronomical telescope described above. In such a telescope, objective lens is replaced by a concave parabolic mirror of large aperture, which is free from chromatic and spherical aberrations. The image formed is much brighter and the reflecting type telescope. Such a telescope is known as Cassegrain telescope, after its inventor. Prism binocular. A prism binocular is an optical equipment which is used for observing distant objects with higher magnification, better field of view, and without lateral inversion. Huygens principle and interference. The ray optics uses the geometry of straight lines to account for the macroscopic phenomena like rectilinear propagation of light, reflection of light and refraction of light, etc. However, the microscopic phenomena like interference, diffraction and polarization could not be accounted for by ray optics. To explain these phenomena, concept of waves was introduced. The new branch concept of waves was introduced. The new branch of physics based on wave concept of light was called wave optics or physical optics. Wave front. A wave front is defined as the continuous locus of all the particles of a medium which are vibrating in the same phase. Depending on the shape of source of light, wavefront can be three types: spherical wavefront, cylindrical wavefront, plane wavefront. Huygens principle. Huygens gave a hypothesis for geometrical construction of the position of a common wave front at any instant during the propagation of waves in a medium. This principle tells the way in which the wave front is propagated further in a medium. Wavelength and frequency. Suppose a source of light is at rest in one medium and an observer is at rest in another medium. Let there be no relative motion between the two media so that geometry of source, medium and observer does not change with time. Therefore, time taken by light to travel between sources and observer is fixed. Behavior of a prism, lens and spherical mirror towards plane wave front. Let us study the behavior of a prism, a lens and a spherical mirror when a plane wave front is incident on them. Behavior of a prism, behavior of a lens, behavior of a spherical mirror. Superposition principle. Superposition principle enables us to find the resultant of two or more wave motions. According to this principle, when two or more wave motions traveling through a medium superimpose one another. A new wave is formed in which resultant displacement y at any instant is equal to the vector sum of the displacements due to individual waves vector y1, vector y2 at the instant. That is, vector y is equal to vector y1 plus vector y2 plus vector y3 plus vector y4 and so on. Clearly, each wave contributes irrespective of the others. Coherent and incoherent addition of light waves. Light waves are electromagnetic waves. The electric vector is responsible for the optical effects of EM wave. To calculate resultant intensity of light due to any number of light sources, we must add suitably the electric fields produced by different sources. Coherent sources. The sources of light which emit continuous light waves of the same wavelength, same frequency, and in same phase or having a constant phase difference are called coherent sources. The phase difference phi between two sources light waves at a given time and at a given position is sum of initial phase difference between two sources A and B and phase difference on account of difference in paths. The latter does not change with time. Hence, initial phase difference between two sources must be constant. Interference of light. When there is a single source of light, the distribution of light energy in the surrounding medium is uniform in all the directions. But when we have two coherent sources of light emitting continuous waves of same amplitude, same wavelength, and in the same amplitude, same wavelength, and in the same phase, the distribution of light energy does not remain uniform in all the directions. At some points, where the crest of one wave falls on crest of other, resultant amplitude is maximum. Young's double slit experiment. Young's double slit experiment. In this experiment, S is a narrow slit illuminated by a monochromatic source of light. At a suitable distance from S, two slits A and B are placed parallel to S. When a screen is placed large distance from the slits A and B, the alternate dark fringes are produced. According to Huygens principle, the monochromatic source of light illuminating the slit S sends out spherical wave fronts. These wave fronts reach the slits A and B simultaneously. Thus, the two waves of same amplitude and same frequency with zero phase difference are given out by A and B. These waves on superposition produce interference. If S is a source of white light, interference fringes are colored and their widths are unequal. Young in 1802 demonstrated the phenomenon of interference of light by a simple experiment. Conditions for sustained interference of light. Following are some of the important conditions for obtaining sustained interference of light. The two sources of light must be coherent. That is, they should emit continuous light waves of same wavelength or frequency which have either the same phase or a constant phase difference. The two sources should be strong with least background. The amplitudes of waves from two sources should preferably be equal. The two sources should preferably be monochromatic. The coherent sources must be very close to each other. The two sources should be point sources or very narrow sources. Color of thin films. A film of a transparent refracting material whose thickness is very small is called a thin film. Combining more than two waves. When more than two sinusoidally varying waves meet at a point, then to find their resultant, we construct a series of phases representing the waves. Draw them end to end, maintaining the proper phase relations between adjacent phases. Draw the vector sum of this array. The length of the vector sum gives us the amplitude of the resultant phasor. The angle between the vector sum and the first phasor is the phase of the resultant with respect to this first phasor. Fringe shift. If a transparent sheet of refractive index mu and thickness T is introduced in one of the paths of interfering waves, the optical path length of this path will become mu T instead of T, increasing by mu minus 1 of T. Diffraction of light. Diffraction of light is the phenomenon of bending of light around corners of an obstacle or aperture in the path of light. On account of this bending, light penetrates into the geometrical shadow of the obstacle. The light thus deviates from its linear path. This device becomes much more pronounced when the dimensions of the aperture or the obstacle are comparable to the wavelength of light. According to Fresher, diffraction occurs on account of mutual interference of secondary wavelengths starting from portions of the wavefront which are not blocked by the obstacle or from portions of the wavefront which are allowed to pass through the aperture. Difference between interference and diffraction of light. Interference is due to superposition of two distinct waves coming from two coherent sources. Diffraction is produced as a result of superposition of the secondary wavelets coming from different parts of the same wave front. In interference pattern, all the bright fringes or bands are of same intensity. In diffraction pattern, all the bright bands are not of the same intensity. In interference pattern, intensity of minima is generally 0 or very small, and there is a good contrast between bright and dark fringes. In diffraction pattern, the intensity at minima is never 0, and there is poor contrast between bright and dark bands. The width of the interference fringes may or may not be equal, but the width of diffraction bands is always unequal. Concept of resolving power. According to ray optics, the image of a point object formed by an ideal lens is a point only. However, because of the diffraction effects, the image of a single point in the object formed by a circular lens will actually be a bright central circular region surrounded by concentric dark and light rings. Resolving power of a microscope. The resolving power of a microscope is the ability of the microscope to show as separate the images of two-point objects lying close to each other. Resolving power of telescope. The resolving power of a telescope is its ability to show distinctly the images of two distant objects lying closely. The limit of resolution of telescope is measured by the angle d theta subtended at its objective by those two distant objects, say stars, whose images are just seen as a separate through the telescope. The value of d theta varies. Directly as the wavelength lambda of light used, and inversely as the aperture, that is diameter d, of the objective of the telescope. Doppler's effect in light. According to Doppler's effect, wherever there is a relative motion between a source of light and observer, the apparent frequency of light received by observer is different from the true frequency of light emitted actually from the source of light. Doppler's effect in light is symmetrical, but the same effect in sound is asymmetrical. Doppler's effect in sound is asymmetrical because a source of sound moving through a material medium in which listener is at rest is physically a different situation from that of a listener moving through that medium when the source is at rest. Polarization of light. Light is an electromagnetic wave in which electric and magnetic field vectors vary sinusoidally perpendicular to each other as well as perpendicular to the direction of the propagation of wave light. Experimental demonstration of polarization of light and transverse character of light waves. The phenomenon of polarization of light can be demonstrated experimentally by a simple arrangement. Nicol prism. Experimental demonstration of polarization of light and transverse character of light waves. T1 and T2 are two thin plates of tourmaline. The ordinary from the sources S is passed through the plate T1 and the light transmitted. When the plate T1 is rotated, the direction of propagation of light as axis, let the second plate T2 be placed in the path of light transmitted from T1. When T2 is rotated gradually, intensity of light transmitted from T2 goes on decreasing. When the crystals are 90 degrees to each other, the light is completely cut off. When the light is reappear, at that time T2 is rotating again. Thus, a Nicol prism is an optical device which is used for producing plain polarized light and analyzing the same. Detection of polarized light. A naked eye cannot distinguish between polarized and unpolarized light. A crystal can be used for making this distinction. A calcite crystal, quartz crystal, a nickel prism can be used as a polarizer as well as analyzer of polarized light. Law of Malus. According to law of Malus, when a beam of completely plane polarized light is incident on an analyzer, the resultant intensity of light I transmitted from the analyzer varies directly as the square of the cosine of the angle theta between plane of transmission of analyzer and polarizer, that is, I is proportional to cos square theta. This rule is also called cosine squared rule. Polarization by scattering. A beam of unpolarized light is incident along z-axis on a scatterer. All the possible direction of vibration of electric vector in unpolarized light is confined to xy plane, as light waves are transverse in nature. Looking in the x-axis, we can see only the vibrations of electric vectors are parallel to the y-axis. Similarly, looking in y-axis, these electric vectors are parallel to x-axis. Hence, light scattered in the direction perpendicular to the incident light is always plane polarized. When a beam of white light is passed through a medium containing particles whose size is of the order of wavelength of light, then the beam gets scattered. When the scattered light is seen in a direction perpendicular to the direction of incidence, it is found to be plane polarized. The phenomenon is called polarization by scattering. Polarization of light by reflection. When unpolarized light is reflected from a surface, the reflected light may be completely polarized, partially polarized, or unpolarized. This would depend on the angle of incidence. If angle of incidence is 0 degree or 90 degree, the reflected beam remains unpolarized. For angles of incidence between 0 degree to 90 degree, for angles of incidence between 0 degree and 90 degree, the reflected beam is polarized to varying degree. The angle of incidence at which the reflected light is completely plane polarized is called polarizing angle or Brewster's angle.